Hello class, these are our Algebra I notes for section 210, connecting equations to graphs. All right, let's go ahead and read. Linear equations can be written in different forms. Some forms allow us to better see the relationship between quantities. So remember, we're using variables to show these quantities or to predict the graph of the equation. Suppose an athlete wishes to burn 700 calories a day by running and swimming. He burns 17.5 calories per minute of running and 12.5 calories per minute of freestyle swimming. So let's just go ahead and read that over again and really get a picture in our heads of what's going on. An athlete wishes to burn 700 calories a day by running and swimming. He burns 17.5 calories per minute of running and 12.5 calories per minute of freestyle swimming. So I'm imagining this athlete, this is a lot of work, right? Running and swimming. It seems like the running burns a lot more calories than the swimming does. Maybe not that many more, 5 more per minute. 700 calories a day seems like a lot. I think about how like my total calorie intake for a day is probably about 2,000. So 700 just by running and swimming seems like a lot to me. Okay, so we are going to, now that we have this picture in our heads, read the next part and see if we can figure out what to do. Let X represent the number of minutes of running. Okay, so 17.5 calories per minute, and I'm going to do that for X minutes. And Y, the number of minutes of swimming. So 12.5 calories per minute, and we're going to do that for Y minutes. Write an equation to represent the combination of running and swimming that would allow him to burn 700 calories. Okay, well, that would be the total calories from running. Total calories from running. Total cal run. Well, that would be 17.5 times X, because it's 17.5 per minute times X minutes. And then we're adding because we're totaling something up. And then 12.5 Y would be our total calories from swimming. So we've got the 12.5 per minute times Y minutes, and then all together it's going to equal 700 is our total calorie goal. All right. We can reason that the more minutes he runs, the fewer minutes he has to swim to meet his goal. And that makes sense, right? Because if you only need to burn exactly 700 calories, if more of them come from running, less come from swimming. In other words, as X increases, Y decreases. If we graph the equation, the line will slant down from left to right. And that's because as we move to the left, our X is increasing, and so the Y decreasing means the graph is going down. If an athlete only runs and doesn't swim, how many minutes would he need to run? So let's think about this. So if he doesn't swim, then that means we are going to substitute 0 for Y, and we're going to find X. So I need to see my equation again. It's kind of up here at the top. So let's go ahead and write that down so we have it right here above where our work's going to go, because I need to move my screen and I want to be able to see that. So you know how I am. I'm always like recopying stuff, make sure I've got it available. Highlight it. It's really obvious now. All right, so let's move our screen back up. Okay. So we want to substitute 0 for Y. So that means we're not swimming. So 17.5 times X plus, and then 12.5 times 0. And this is going to equal 700. So then what that means, 12.5 times 0 is just 0. So we're going to end up with 17.5x equals 700. And we'd have to divide both sides by 17.5. So this is where you can't see, but I am grabbing a calculator. And if we do 700 divided by 17.5, we get 40. So if he's only running, he needs to run for 40 minutes, and then he doesn't have to do any swimming at all. So because the 40 was our X, and we had 0 for y. Remember, ordered pairs are x comma y. This means on my graph, this combination of times is 40, comma 0. And we call it the x-intercept. And we'll look at why that is in just a second. If he only swims and doesn't run, how many minutes would he need to swim? So now we're going to say 17.5 times 0 plus 12.5y equals 700. So this is going to take more minutes, right? Because it seems like we burn quite a bit more calories, 5 more calories. So maybe almost a quarter more, third to a quarter more by running than we do swimming. So it's going to take more time. So because that's zeroed out, now we only have 12.5 times y equals 700. And then we'll divide both of them by 12.5. And we get, let's see, y equals 56. So if he only wants to swim, he would have to swim for 56 minutes, or she would have to swim. I don't remember who we're working with here. Oh, it says he, an athlete, he. Okay. So this is going to be the point. Let's see, we put 0 in for x, and we had y equals 56. So 0, comma 56, and that is the y-intercept. All right, let's go ahead and look further at our notes here. If an athlete wants to know how many minutes he would need to swim if he runs for 15 minutes, 20 minutes, or 30 minutes, he can substitute each of these values of x into the equation and solve for y. Or he can first solve the equation for y. So that's going to be looking at these, and I need to write my equation again, but that's going to be rearranging our equation, solving for a variable like we've done the last couple days. 17.5x plus 12.5y. So let's write that down first. 17.5x plus 12.5y equals 700. And then we want to go ahead and solve that for y. So let's go ahead and do that. So if I'm solving for y, then the term, that part that has x, this little piece of it, 12.5x, I want to go ahead and subtract on both sides. Or sorry, 17.5x. I might have said the wrong thing there. So the 17.5x is being subtracted on both sides to zero it out. So now I'm getting closer to having y by itself. Now I only have 12.5 times y equals all the stuff on the other side. Remember, it doesn't equal just a number. It equals the expression 700 minus 17.5x. And then our last step would be dividing both sides by 12.5. So let's go ahead and scroll up. So now we have y equals 700 minus 17.5x divided by 12.5. And I don't like the way this is simplified. I think what we're going to have to do is we're going to have to do a little bit of work. So let's go ahead and erase this. It just doesn't look like an equation that we would graph. And let's figure out the 700 divided by the 12.5. We're going to distribute this division. And the 17.5 divided by the 12.5. Let's go ahead and reduce those down. So if I do that, I'm going to move over to the right here. I have y equals 700 divided by 12.5 was 56, minus when I divide 17.5 by 12.5, I get 1.4x. All right, so let's kind of rewrite this. So that equation is written in, and I'm going to do one more step. I'm going to put the x part first, negative 1.4x plus 56. So now I can see real clearly I have a slope and I have a y-intercept. So that means my slope is written in, my equation is written in slope-intercept form. So again, that's y equals negative 1.4x plus 56. So my coefficient of x is the slope of the graph. Is the slope. Okay? And what that means is that because it's negative 1.4, it means as x increases, we should have done bulleted points here, increases by 1. So that's going to go to the right. Y decreases or falls by 1.4. For every additional minute of running, the athlete can swim 1.4 fewer miles. For every additional, because x is our minutes of running, the athlete can swim, so he can swim 1.4 fewer minutes. And I think I am going to switch this first one to a bulleted point to match the rest. So the x coefficient is the slope, and it's negative. We could think of the graph falling from left to right or going down. So as your x is increasing by 1, it falls by 1.4. So when we say falls by 1, if you could think about having that fraction here and putting it over 1, right? So my top number, my change in y is negative 1.4, my change in x is 1. So I think it really helps to be able to see that fraction. So we're really trying to have a deeper understanding right now of how graphs work. So the constant term is the y-intercept. And it tells us the number of minutes the athlete would need to swim if he does no running. Okay, so I want to add a couple things here. I first want to say when x equals 0, because that's also our y-intercept. And then when x is 0, that of course is when we do no running. So if no running, the number of minutes the athlete would have to swim. So the first equation we wrote, so that was 17.5x plus 12.5y. So it turns out I have it memorized by now, equals 700, is a linear equation in standard form. So we rearranged it to come up with slope-intercept form, but to start out with it was in standard form. In general, it is expressed as ax plus by equals c, where x and y are variables, and a, b, and c are integers. And a lot of times we like it if a is not negative. I will take negative answers for a, but not negative is better. So our goal is that a, b, and c are not fractions, is what we're really after. They are integers. Like 5 or 7 would be okay, or negative 8 would be okay, but we don't want a to be like 1/3. The two equations are equivalent, so they have the same solutions and the same graph. So we're going to go ahead and graph, and our x, of course, is our minutes of running. And our y is our minutes of swimming. I missed a letter in the word running, which is pretty bad. I had so many n's already, I didn't put the last one in. Okay, and this is minutes of swimming. min of swim. And we're going to count by eighths. So 8, 16, 24, 32, 40, 48, 56, 64. That should be plenty. We'll do the same thing for our number of minutes or our y scale. So if I look at data I had on the first page, I had a couple pieces of information. So one of them was that I had this point, 40, 0, for running 40 minutes and not swimming at all. I also have this point 0, 56 for not running at all but swimming for 56 minutes. So we're going to go ahead and plot both of those points, 40, 0 and 0, 56. So 40, 0 would be right here. That's my 40, 0. And again, that represents running for 40 minutes and not swimming at all. And then we've got the other extreme if we only swam, and only swimming would be at 56, 0. And remember that's 0, 56. Almost screwed that up. So remember 0, 56 is when x is running. So when we run 0 minutes, we would have to swim 56 minutes. And remember, we always end up having to swim more than we run in that case because the running burns a lot more calories. And then now that we know we have these 2 points on our line, we're just going to go ahead and connect them. Now that is a really awful wavy looking line. I'm going to give it one more chance on the surface here because that looked pretty messy. I did a practice run and it looked so good and I thought I was ready and then I screwed it up. So let's try one more time. Much better. 56, 0. The two equations are equivalent, so the equations would have the same solutions and same graph. So by two equations that are equivalent, we mean the 17.5x plus 12.5y equals 700. That's how I just graphed it. But remember, we could also write y equals negative 1.4x plus 56. And it is really hard to see a slope on this graph. I like the word problem. It helps us make sense of what's going on here. But the numbers, the negative 1.4 slope in particular, make it really difficult to see what's happening with these kinds of numbers. But they are equivalent. They do give you the same graph. It's just different ways of writing the same equation. As always, if you need help, make sure you're getting it in class.